Welcome to Why Is That, Dad? The show that takes your children's toughest questions and opens them up to the entire universe. I'm your host, Phil, and today we have my daughter, Cecilia, creator and eyeglass wearer extraordinaire.
Hey Dad, we need to have much better podcasts than Dominic's. I thought the honey badger was pretty cool, but we can outdo him.
I have a pretty interesting show today. Before I start, be sure to give us a 5-star rating on your podcast app and share this with a friend. And do it now, before you change your mind. We just started that podcast, and my kids and I are super excited to share it with as many people as possible. We're aiming to publish a new episode every Tuesday, so look for us then. I want to segue into this by starting off talking about a backpacking trip I'm hoping to take next week, a 15-mile hike. Fall is the best time for backpacking. The cooler weather, water is back in the streams, the colors of the leaves against the backdrop of the bright blue sky. It's beautiful.
Yeah, breathtaking. The colors really make it special. The leaves are only those awesome colors in the fall. But the sky, it's always such a beautiful blue. Why is that, Dad?
Well, the simple answer is that the sky is blue because of the way light hits our atmosphere. Now, a common misconception is it's just the ocean reflecting its blue into the sky, but if you look at the sky over the massive Sahara Desert, it's still blue. The truth is much cooler. You see, sunlight looks white, but it's actually made of all the colors of the rainbow. Here's the key. Light travels in waves, and each color is a different wavelength. Think of a wavelength as the distance between two consecutive peaks on a wave. In the visible spectrum, the light you can see, the length of that wave determines the color. Red light has a long wavelength, meaning its waves are long and lazy, like big ocean swells. Blue light, however, has a much shorter wavelength, meaning its waves are small, quick, and tightly packed. When that white light smashes into the tiny invisible air molecules, mostly nitrogen and oxygen, the short, quick blue wavelengths get scattered everywhere, bouncing into your eye no matter where you look. The red and yellow light, they're the longer, lazier waves, and they mostly cruise right on through.
But why do the short blue ones bounce around so much?
That is a perfect follow-up question. The name for this principle is Rayleigh Scattering, and it's all about size. Specifically, the size of the air molecules versus the size of the wavelength. Imagine, the atmosphere is full of marbles, our gas molecules. Blue light waves are like small, speedy pebbles. Their short wavelength makes them the right size to easily hit those marbles and get deflected across the sky. Red light waves, however, are like basketballs. They're so much bigger than the marbles that they usually fly right past without being bothered. The shorter the wavelength, the more it scatters. Now, for a deeper dive, technically, violet light has the shortest wavelength, so it scatters even more than blue. So why don't we see a violet sky? That's a fascinating combination of physics and biology. First, the sun simply puts out a little less light in the violet part of the spectrum. Second, and more importantly, our human eyes are just less sensitive to pure violet. We end up seeing a mixture, and our brain processes that mixture as the beautiful blue we know. This process also depends on the density of the air. If you ever hike high up on a mountain, like we're going to do next week, you'll notice the sky looks as much deeper, darker blue. That's because there are fewer air molecules up there, so less blue light scatters. The lower density gives you a darker and more dramatic blue canvas. And here's the best part. This also explains sunsets. At noon, the sun's light travels a relatively short path through the atmosphere. But at sunrise, or sunset, the light has to travel through the absolute most atmosphere to reach your eyes. This long journey means all of the short wavelength blue light is scattered away well before the light reaches you, leaving only the long wavelength colors, the reds, oranges, and yellows, to make that incredible display we see near the horizon. It's the same scattering phenomenon, just amplified by distance.
Okay, so the blue bounces, but did people always know that the teeny gas was doing it?
You're asking a history question now, and the answer is no, they didn't. This mystery baffled the world's greatest minds for centuries. The ancient Greeks had no idea, just assuming the air was naturally blue. Even the Renaissance polymath Leonardo da Vinci thought the blue was caused by tiny water vapor particles in the air. He was very close, but no cigar. It wasn't until the 1870s that a British scientist named John Strutt, also known as Lord Rayleigh, finally solved the puzzle using mathematics. He proved definitively that it wasn't dust or water, but the individual microscopic gas molecules themselves that were doing the scattering. Lord Rayleigh was a true genius, a polymath who worked on everything from acoustics to chemistry. In 1894, he was part of the team that discovered argon, a noble gas found right there in the atmosphere. So the man proved why the sky is blue also helped discover one of the key ingredients, a key scattering agent of the atmosphere itself.
If it's the atmosphere that's responsible for the blue, is the sky blue in other atmospheres, like other planets?
That's a rather arbitrary question, but an interesting one nonetheless. It really depends on the planet. Uranus and Neptune have blue skies due to their methane atmosphere, but not Mars. So on Earth we have Rayleigh scattering. On Mars there is something called Mie scattering, M-I-E. This happens because the Martian atmosphere is thin and filled with massive amounts of fine, reddish-brown iron oxide dust, the same rust that makes the planet look red from space. These dust particles are so large, many times bigger than the light waves they scatter, that they don't care about the color of the light. They scatter all the colors of light, but they scatter the long wavelengths forward. This leaves the sky looking washed out with a yellowish butterscotch color during the day. The sunset on Mars is the complete opposite of Earth. As the sun dips, the light has to travel through more of that thick dust, which filters out that red and yellow light near the horizon. This allows the blue light to concentrate around the sun, creating a strange ethereal blue glow in the Martian twilight. It's a whole different kind of physics show. Okay, let's climb back out of that dusty Martian atmosphere and get back to our beautiful Earth sky.
Wow, so blue is not that uncommon as a sky color. What about other aspects of the natural world? I never see blue leaves or flowers. Why is that, Dad?
Well, blue is profoundly important and yet surprisingly rare. Did you know that in nature, blue is often a trick of the eyes? For almost all flora and fauna, bluebirds, blue morpho butterflies, their color isn't from a blue pigment. It's structural color, created by tiny, precise layers or prisms that scatter and reflect blue light, just like the sky. The most fascinating exception is a tiny creature called the olive-winged butterfly. This rare insect is one of the very few organisms that actually produces a true blue pigment, specifically a compound called terobilin, highlighting just how difficult it is for life to manufacture this color. One other being the mandarin fish. There are some blue flowers like delphiniums that appear true blue through a pigment called delphinidin, but it's exceptionally rare, which has led many rose breeders on a centuries-long quest for a blue rose, which is only possible due to genetic engineering.
Dad, what do you mean blue is rare in nature? It's everywhere. We have blue jays in our backyard. I've seen peacocks at the zoo. I've watched wildcats in National Geographics, and they show blue-tailed skinks and hyacinth macaws. And I know I've seen blue flowers, although I don't know which one.
Those appear blue, but many of those are an illusion. Again, most of them utilize some kind of structural coloring where the light is scattered in such a way that it appears blue, or, as is the case with the aforementioned delphinidin, it's actually a red pigment which has its surrounding pH changed, which chemically modifies that delphinidin. It's not a blue pigment. And before someone gets too pedantic and says that all color is just an illusion and a trick of the light anyways, colors play a real and significant role in human culture and society. In order for us to use those colors, we need to extract them somehow. So when I mention something not really being blue, I'm talking it's not due to a blue pigment. If you crushed up those blue feathers or even blue berries, you won't get blue. Compare this to something like red. Red feathers or red berries have a red pigment, carotenoids, which are found in abundance in nature. This isn't to say that only blue utilizes structural coloration for colors, but it's considered the rarest natural color. And even the blues that you can get from nature, they don't last long enough if extracted for something like paint pigment. They fade quickly then when extracted and exposed to sunlight.
But I've seen blue in old art. Even the Egyptians used blue, like on King Tut's funerary mask. So they must have gotten it from nature. Or aliens.
No, it wasn't aliens.
Then what was it?
You're right about the Egyptians. This rarity of blue meant that for centuries, getting a stable blue pigment was almost impossible. In ancient times, the Egyptians revered the semi-precious stone lapis lazuli. This stone was mined in Afghanistan, ground into the pigment ultramarine, and shipped to Europe. The name literally means beyond the sea. It became so rare and so expensive that it was, pound for pound, worth more than gold. To put this in modern terms, a pound of the refined pigment was easily valued at over $64,000 during the Renaissance, in today's dollars, and sometimes even more expensive. This expense gave the color a divine significance. The Catholic Church actually reserved this costly pigment for painting the robes of the Virgin Mary in Renaissance art, using the expense to visibly symbolize her celestial importance and purity, a visual connection to the expensive color of the heavens. This all changed in 1706 with a happy accident involving a German chemist named Johann Jacob Diesbach. Diesbach was working in Berlin for a dye maker, trying to create a red pigment, specifically a cochineal lake. He was using potash contaminated with animal blood. Instead of red, though, the combination of the iron from the blood and other chemicals resulted in a brilliant, deep blue pigment, Prussian Blue. This accidental discovery suddenly made a stable, vibrant blue accessible to all painters, revolutionizing art and ending the pigment's status as a luxury reserved only for the elite. Beyond art, blue carries a deep meaning. It's often used as the color of calm and serenity, but it's also the color of sadness. We feel blue or sing the blues. The importance of the color is undeniable.
That makes sense about the color, but why are some people's eyes blue then?
That's a perfect final why question. Just like the sky, blue eyes don't actually contain blue pigment. Blue is the rarest eye color, and the blueness is created by the Rayleigh scattering, like we talked about from the beginning. The outer layer of the iris has low melanin, and when the light hits that layer, it scatters the blue wavelengths back out. It's an optical illusion. You should care about all this because the sky is your greatest, most permanent science and philosophy lesson. Knowing this teaches you two big things. First, it shows you that the color of our world is kind of an illusion, created by physics that you can learn and understand. Second, it gives you the tools to analyze everything around you. The next time you look at a cloud, it's white because the water droplets and ice crystals are large, causing Mie scattering, which scatters all colors equally. From the blue sky to the white cloud to the sunset, you now understand the difference between particle size and light waves. You can now analyze the sky like a true scientist. Keep asking why. Before we go, Cecilia has 3 trivia questions for you all based on today's episode.
Okay, audience, listen up. If you know the answer, post them in the comment section and we'll read your name during the next episode. Unless you're shy, then give your dog or cat's name instead. What is the specific name of the principle that explains why our atmosphere scatters the short blue wavelengths of light more than the long red ones? Which Nobel Prize-winning British scientist, also known as Lord Rayleigh, was the first to mathematically prove why the sky is blue? What color is the sunset on Mars, and which scattering principle explains why it is that color? Okay, and a special shout out to the listeners who posted the correct answers to the last episode. Vinny and Petra, way down in Maryland.
Awesome. Good job, Vinny and Petra. That's it for this week. I hope you all enjoy this journey with us today. If you love this episode, please take a moment to give us a 5-star rating on your podcast app. It really helps us out. And for more fascinating dives into what it's like raising a big family, be sure to check out our YouTube channel, Contemplative Chaos. Join us next time on Why's That Dad, where we'll explore another one of life's intriguing questions. Until then, keep looking up, keep asking questions, and keep exploring. God bless.